sorry, let me just get rid of that. Who have not come across how one can do cosmology with gravitational waves. So it starts off quite simply, and I hope that's okay for everyone. So here I'm showing you a cartoon of the evolution of the universe from the very beginning, at the initial singularity, through a period of possible inflation, so exponential expansion of the universe. So then there's the formation of the cosmic microwave background. And then as the universe expands, galaxies start to form. And here we are at late times with possible dark energy accelerated expansion. So the question I want to try and answer is how can cosmology or gravitational waves, teach us about the expansion of the universe and cosmology? So in fact, as we'll see, it can do that in two different ways in a sense. Okay, so this was, here we are. Okay, so the first way that we can probe cosmology with gravitational waves is by looking at the gravitational wave signal from individual sources. So in practice, we'll be talking about systems of binaries at cosmological distances. And in this way, we're going to learn about the properties of the late time universe. So in other words, the properties of the late time universe here, closer towards today. And we will learn about the properties just because these gravitational waves emitted from binaries are traveling cosmological distances. And so as they travel these cosmological distances, from what we observe, we can actually try and learn about what's happening in between their emission and our observation. So what are the individual sources that we're going to be focusing on? So there'll be binary neutron stars, BNSs, binary black holes, BBH, and a binary made of a neutron star and a black hole. And as you've seen in other lectures, the LIGO-Virgo collaboration has already seen a number of these different events. Well, in practice, one binary neutron star event, GW17817, with its electromagnetic counterpart, but also some other binary neutron stars with no electromagnetic counterparts. And in the latest LIGO-Virgo catalog, there are some 39 events consisting of these three different types of binaries. And why can we do cosmology with these is because these sources are at very large distances of the order of 5 gigaparsecs, which in terms of redshift means something of order 0.75. So since I want to do cosmology with these, let me just set the scene and just say more precisely what I want to do in the context. So just let me say that I'm going to assume throughout these lectures that we're working with a flat Friedmann-Robertson-Walker-Lemaitre universe. So here's the line element, minus dt squared plus a squared of t dx squared. So a is a scale factor. And from the scale factor, we can define the Hubble parameter h as a function of time. So it's a dot over a. So it has dimensions of 1 over time. And the redshift is defined in the usual way as 1 plus z, which is the scale factor a evaluated today, t0, over the scale factor at time t. And I should also say that mostly I'll be assuming that general relativity is the correct theory of gravity, and it's valid on all scales, including cosmological scales. Okay, so with these observations of individual sources, what quantities are we after regarding the late time universe? So let's rewrite the Hubble parameter, h of t, but now in terms of redshift. So here it is on the left-hand side. So h is a function of redshift. And this expression comes from the Friedmann equations, where I'm neglecting the component of radiation, which there is in principle early in the universe, because we're looking precisely at the late time universe. So what are the quantities that we're going to want to determine with gravitational waves? So there's the first one, which is the Hubble constant, and it has dimensions of 1 over time. And it characterizes the local time scale in the universe. It's really a fundamental parameter. It fixes the time scale, and its inverse fixes the distance scale, which is of order gigaparsec. So that's something we're going to be after. Another quantity we can be after is omega m, which is the energy fraction in matter today, so its value. Then there's a contribution here from possible dark energy or a cosmological constant, which is described by an equation of state W of Z. So that's the equation of state of dark energy, which is its pressure divided by its energy density. So something else that we can be after is how this quantity W, well, already what its value is today and how it evolves with redshift. So for those who are not so familiar with dark energy, let me just say a couple of words about dark energy. So where does it come from? So as you all know, the universe is expanding. And since gravity is meant to be an attractive force, one would expect that the expansion of the universe would actually decrease with time because of the attraction. And so one would expect deceleration. In other words, we would expect that in the past, objects were going faster. So I've tried to draw that on this diagram, which shows the velocity of nearby objects as a function of distance. So the larger the distance is one looks at, the further back one's looking at in the past. And since gravity is attractive, one would expect velocities to decrease with time, right? So they're larger in the past and decreasing. But in practice, what one observes is exactly the contrary, that objects were slower in the past, and so the expansion of the universe is accelerated, which is what, of course, what the Nobel Prize in Physics was awarded for in 2011. And so the question is, how do we source this recent acceleration, which can't be from ordinary matter, and it can't be from dark matter. So the dark energy which we'd like to probe with gravitational waves is something that we introduce to try and act as a source of this acceleration. And what do we know about dark energy? Well, not very much, really. I mean, it doesn't interact directly with us, which is why it's known as dark. It's diluted everywhere with an energy density we can work out as given that we know how fast the universe should be accelerated today, and it's absolutely tiny. If you calculate in terms of the weight of a mosquito, well, it's 1 mosquito per 10,000 kilometers cubed. And we don't, as I said, we don't know much about it, but we know what it isn't, which, for example, is not the contribution of the Higgs boson to the vacuum energy. So if you take the mass of a Higgs boson per Compton wavelength cubed, you get a number which is much bigger. And of course, this is a cosmological constant problem. It's not that I made a sign mistake here. It's that there really is a huge factor, a difference in factor. Okay, so with gravitational waves, maybe one can also probe, or we can try and probe the equation of state of dark energy. Now, of course, there are other things that one could do also. Maybe one can use gravitational waves from these individual binaries to test possibly modified gravity. And as you heard in other lectures, the idea of modified gravity is to get rid of, in a sense, of this dark energy and put it into a modified evolution equation or modified properties of gravity on the very largest scales. And something else that we can learn about with gravitational waves at these late times is about astrophysics. We can learn about the origin of perhaps of black holes. And maybe an important message, which I can take away message from this talk, will be that in fact, doing astrophysics and working or learning about cosmological parameters such as the Hubble constant are actually two things which will have to go, I think, hand in hand. You can't try and learn about, for example, the Hubble constant, neglecting astrophysics completely. And that's, I think, an important point which I'll stress towards the end of today's lecture. Okay, so we can learn about the late time universe. So the Hubble constant, the energy fraction of matter in the universe, maybe the equation of state of dark energy, possibly modified gravity and astrophysics by looking at individual sources of gravitational waves. But what else can we do with gravitational waves? The other thing we can learn about are the properties of the very, very early universe. So right at the beginning of the universe. And in this case, we can't look at individual sources because they're too far, so they're too faint. But we can look at the signal, superimposed signal of all those sources at very large distances. And those are summarized, or those will appear as a stochastic background of gravitational waves. So the stochastic background of gravitational waves is the analog of the cosmic microwave background of photons. So it's a superposition of waves coming from random directions at random times, and they overlap that you can't resolve the individual waves. But there's a fundamental difference between the background of photons and the stochastic gravitational wave background of gravitons, which I'll mention in a second. But maybe first we can talk about the possible sources of this stochastic gravitational wave background. So the sources are from very, very, very early in the universe. So it could be, for example, the inflationary period, which I mentioned before, right after the very, very early in the history of the universe, before the CMB was formed. It could be possible phase transitions, which occur very early in the universe and are predicted by some particle physics models, such as grand unification. So these generally proceed through the nucleation of bubbles, and those bubbles will expand, and through their expansion and collision, they can emit gravitational waves. Or there could be topological defects, such as cosmic strings, which I've pictured here, which exist in the universe and also generate gravitational waves. And all of these sources from processes which are extremely early in the history of the universe and about which we can learn if we can detect the stochastic background of gravitational waves. So I said that this stochastic background is the analog of the cosmic microwave background of photons, but there's a crucial difference. So what's the crucial difference? And it's due to the time at which this background is formed. So let's try and understand where that comes from. So let me remind you that particles, in cosmology, when particles decouple from the primordial plasma, so at some time T decoupling or corresponding temperature T decoupling, they give us, it's like they give us a photo or a snapshot of the state of the universe at that time. The reason is that before that they're coupled, and so all the interactions between them will, I mean, they'll tend to thermal equilibrium. All the interactions between them will obliterate all information. So the decoupling time gives us, oops, do you see that or no? Okay, a snapshot of the picture of the universe at that time. So how can we calculate the decoupling time? Well, particles are going to be in thermal equilibrium when the rate of processes maintaining thermal equilibrium is larger than the Hubble expansion rate. Now, the rate of processes maintaining thermal equilibrium is essentially given by the number of density of the particles n, their cross-section, interaction cross-section, times their typical velocity. And the particles will drop out of thermal equilibrium when the expansion rate, h, is of the order of gamma, so the rate of microscopic interactions maintaining thermal equilibrium. So if one equates these two quantities, then you can determine the decoupling temperature. So one can do that, this calculation, it's a very simple calculation. If you assume relativistic particles at temperature T, the number density of particles is T cubed. The velocity of the particles is the speed of light, which is 1 in my units. And from the Friedmann equation, the energy density in relativistic particles goes as T to the 4th. So you know exactly the temperature dependence on the left-hand side. And so you can use this to estimate the temperature of decoupling. So for neutrinos, one can do this exercise. The cross-section is given by the Fermi constant. And so you can work out that neutrinos will decouple at 1 MeV. And the same calculation for gravitons, for which the cross-section is determined by Newton's constant, the gravitational constant, gives you that gravitons decouple at the temperature of the order of the Planck temperature. So in other words, for gravitons, decoupling occurs at the Planck scale, as opposed to CMB, where the decoupling temperature, as we said here, is of the order of 3000 Kelvin. So basically, gravitons are decoupled at all times, which means that since they're not in equilibrium, they don't lose memory of the conditions which produce them, and they'll retain their spectrum, shape, frequency, and intensity of physics at the corresponding high energy scale when they were produced. So I've heard this being described in a sort of more everyday language, which is that if you think of a child, okay, and you see a child at the age of 6, for example, you have a picture of the child at the age of 6, and you know the child's evolution after the age of 6 to when it was an adult. You can try and guess what the child would have looked like as a baby. Okay, if you've never seen the child as a baby, if you know the child from the age of 6 and onwards, you can try and guess what it would look like as a baby. Well, that's the situation with the cosmic microwave background of photons. You can see the child or the universe from a certain age and onwards, and you can use it to try and determine what the child was like as a baby, but you can't actually see it. You never saw it as a baby. Whereas with gravitational waves, it's like seeing the child from being a baby from its very first day. You can see all its evolution from the beginning. So it's much easier to learn about the properties of your child, or in this case of the universe. Perhaps the analogy is not very good. Anyway. Okay, so in other words, so this is the same picture as at the beginning, but unfortunately the direction is inverted. So we now read from right to left. So the CMB, cosmic microwave background, tells us about the evolution of the universe from temperatures of order the electron volt, whereas the gravitational wave background will tell us about the evolution of the universe from the very beginning. So if we can detect it, which is a difficult thing to do, then there's a huge potential to bring information on high energy phenomena in the early universe before the CMB. Okay, so to summarize this introductory part, with gravitational waves, we can learn about the late time universe by looking at the gravitational or detecting gravitational waves from individual sources. So as I said, the expansion rate of the universe, the Hubble constant, omega m, dark energy, and astrophysics. And in a complementary direction, we can learn about the very early universe at times beyond the Planck time through the stochastic background of gravitational waves. And this will teach us about many interesting phenomena, such as what happens during inflation, phase transitions in the early universe, and topological defects. So I've divided these lectures into two corresponding parts. So there's the part on late time cosmology, which will be today's lecture and maybe part of the next one. And then the second part will be on the very early universe with gravitational waves. And this part on late time cosmology, I've subdivided again into 6 sections. So the first one, I'd like to try and summarize what's the current status on cosmological parameters, such as the Hubble constant. Then in the second part, since we want to use the observational gravitational wave signal from binaries, I just want to give a brief summary of the characteristic scales which are involved. So what are the mass scales of these binaries that we're interested in, depending on the detectors that we're going to be using. Then we'll discuss the gravitational waveform emitted by these binaries in an expanding universe. The fourth part will be how we can measure distances with these binaries, and especially with what accuracy, which will be something very important to determining the accuracy with which we can measure cosmological parameters. Then there'll be a discussion as to how we can determine the redshift of our gravitational wave binaries. And I'm going to focus on 4 different methods to determine the redshift. And then if there's time today, but I doubt it, we'll talk about tests of modified gravity with gravitational waves. Okay, so let me start with a brief summary of the status of cosmological parameters and why it's very important to try and approach or measure these cosmological parameters with gravitational waves. Okay, so the status of the value of the Hubble constant, which, as I said, sets the timescale of the expansion of the universe today. So what's the status of the value of H0? So I think this plot, which is taken from a paper by Wendy Friedman, summarizes the situation very well. So on the y-axis is the Hubble constant. So as I said, it has units of time, but it's useful to measure it in kilometers per second per megaparsec. So the distances cancel out to give in 1 over time. So it's the value of the Hubble constant as a function of the publication year of different papers. And it focuses on 2 different methods to measure the Hubble constant. So in blue, a method's determined from the Hubble Space Telescope or the SHOES collaboration. So here they try and measure the Hubble constant as I'll explain in a minute, but by using the properties of certain standard candles, so Cepheid variables and supernovae. And the errors in those measurements have decreased with time. And we're today at a value of H0 of approximately 74 in these units. And the red data, on the contrary, so it's still measuring the Hubble constant, but it's using actually physics of the very early universe, so CMB physics. And to relate the physics of the very early universe to today, one has to assume something about the evolution of the universe. And the assumption is what's known as the standard lambda CDM model. So lambda CDM means that the equation of state of dark matter is -1. So dark energy behaves like a cosmological constant. And the value of the Hubble constant that they get has also been involving time with errors that decrease. And the value is of order 67.74. So as you can see, these 2 values don't agree within the error bars. And just to give an idea of the fact that in fact the error bars and the values of the Hubble constant have really been varying in time. Down here on the left, you can see the very first value of the Hubble constant measured by Hubble himself. So in the same units, he found 500. Okay, so it's a complicated measurement to make, and the values, have been varying. This is the situation today with at least 2 experiments, and they don't agree to within a few sigma. Okay, so just a couple of words about how the value from the Hubble Space Telescope collaboration is carried out. So it's based on the fact that Hubble's law, if you want. So the velocity of the radial Hubble velocity, so VH of galaxies as they're moving away from us, is related to the Hubble constant times the distance to those objects. And the problem is that measuring distances in cosmology is really very difficult because you can't take a ladder or a tape measure and go from one galaxy to the next to work out how far it is from you. So the standard method is to measure these distances is somewhat complicated. It involves setting up a so-called distance ladder. So there are a number of steps to it, or a number of rungs to use the jargon. So the first one is to use parallax. So how the objects, close by objects seem to move relative to the far distant stars as a function of the Earth moving around the sun. So you measure the distance to those using parallax, and you focus on very special objects whose intrinsic luminosity you think you know. So in particular, Cepheid variables. So that gives you, you can measure those distances using parallax. Then you look at, you look for the same type of objects, so Cepheid variables, for example, in more distant galaxies. And since you're meant to know their luminosity, from their observed flux, you can then determine their distance. Then in those more distant objects, you hope that there are other type of standard candles, so supernovae, and that enables you to measure the distance to those supernovae because you calibrate them with the Cepheid variables. And then you look for even further distant galaxies, which also host the same type of standard candles, so supernovae. And from their observed flux, you can then measure the distance to those more distant galaxies. So it's setting up different rungs of a distance ladder in different ways. And you have to, I mean, it's a tricky thing to do. And it's possible to make errors, right? So that's how one measures distances in the sort of in a sort of more standard way in cosmology. So that gives you the distance, and then as for the left-hand side here, it depends on the expansion rate of the universe. So it depends on the redshift, and the redshift you measure simply using the Doppler effect. Okay, the redshift, the light is redshifted by the expansion of the universe, or photons lose energy as they propagate through the expanding universe. So once you know the redshift and you know the distance, then you can divide one by the other and determine the Hubble constant. And this other plot from a very nice paper, summary paper up here, summarizes the status of the so-called Hubble constant tension. So there are the values so determined from CMB physics, early universe physics, assuming, as I said, lambda CDM model. And then there are those using the distance ladder, so from the Schu's collaboration, the one I already mentioned. And of course, since then, there have been others using independent methods with the aim of trying to understand which of these values is correct, or if both are correct, and what would mean. So yeah, the interesting question is, well, there are a number of interesting questions. Is this a real discrepancy between these different values, or is it due to some unknown systematic error? If it's a real discrepancy, why is there this discrepancy between two measurements of the same, in principle, the same quantity? Is it due to physics beyond this standard cosmological, standard lambda CDM model? Could it be due to modified gravity, for example? But anyway, the long and the short, I think, is to say that it's extremely important to have independent ways of measuring the Hubble constant. And that's what gravitational waves can do for us. And as we'll see, gravitational waves enable us to measure the distance in a completely new way. So without using the distance ladder, constructing this distance ladder, gravitational waves gives us a direct way of measuring the distance. And so provided we can then work out the Hubble velocity, or the redshift, corresponding redshift of those gravitational waves events, then we can determine the Hubble constant using gravitational waves. And so here's the first result of the measurement of the Hubble constant using the binary neutron star GW 170817. So this is the posterior probability distribution. So it's the most probable value of H as a function of H. And there are two lines here. So the green line is the CMB value of H0. The orange line is the one measured by the Schu's collaboration. So as we saw, they didn't agree. And this is the one measurement from gravitational waves. So with one measurement, as opposed to hundreds of supernovae, for example, here, the pretty amazing thing is it gives you a value which is kind of in between these two, but the errors are very large. Okay, the value is 69 plus 17 minus 8. And one of the purposes of these lectures is to explain to you why these errors are large, and also try and explain how we can reduce those errors. And one way of reducing those errors will be to have many events, not just this one event, gravitational wave event. Okay, Danièle, so yes.
There is a question.
Please.
Luis, maybe you want to...
Hello, can you hear me?
Yes.
Yeah.
I'm just wondering about this Hubble tension. How do these two different, and now the measurement with GW event, how do they depend on the assumption that is a lambda CDM cosmology?
They don't. The answer is that they don't. There's no assumption. So I think, okay, so let me go back. So as I said, one of the things that we should be able to measure with gravitational waves, amongst other things, is the, is the equation of state of dark energy. Okay, so there's no need to fix that. There's no assumption that it's equal to -1.
Okay, thank you.
If that answers your question.
It does. Okay. Thanks.
There's another question.
Yep.
Sang?
Hello?
Yeah.
Thank you. I'm just wondering about the Hubble constant, the formula VH equals H times D.
Mm-hmm.
And especially the local measurement at the late time universe.
Mm-hmm.
So distance is measured from independent way, but about the velocities of those sources with the late time cosmologies may be affected by the so-called the peculiar motion, which is not entirely due to the expansion of the universe. How well do we understand the velocity component, the peculiar velocity components when we actually measure the Hubble constant? For example, VH equals actually H naught times D plus some peculiar velocity contribution. How well do we understand that in that measurement?
Right. So the you're right. So of course, when you determine this posterior distribution on H0, there are a number of errors which you have to take into account. Okay, one of which is precisely the peculiar velocities. Okay, which are essentially how well we know the velocity here, because as you said, there's a component which is not from the Hubble expansion, but from the attraction or peculiar velocity, the attraction to other gravitational force with other nearby objects. And so that will be a contribution to the error budget on H0. But as we'll see, or I'll try and explain to you later on, in fact, that contribution is absolutely negligible relative to the contribution coming from the error in the distance measurement. So you're right, it has to be taken into account, but it turns out to be rather negligible, even for nearby objects, relative to the error on the distance measurement.
Okay, thank you.
Okay. Right, so now let's go on to trying to understand how one can measure the distance with gravitational wave measurements. And I think it's probably useful to try and bear in mind what are the characteristic scales of the problem. So in other words, here I want to just think a little bit about what are the distance scales that we can measure. So given to a binary composed of a mass m1 and a mass m2. And so what distances can we measure given these two masses and given a detector that we have in mind? So as you've heard in previous lectures, we could be thinking about the LIGO-Virgo network, which for which the characteristic frequencies of the order, well, somewhere between 10 and 5 kilohertz. We could have in mind the future Einstein telescope detector, for which the characteristic frequencies are somewhere between, well, they're similar, but there's a slightly lower frequency band here. So they're sensitive to it's sensitive to a lower frequency, 1 hertz relative to 10 hertz here. That will be very important later on. And a slightly higher frequency, well, they're the same order, the upper frequency. Or we might have in mind the future LISA detector, which, as I think you all have heard also in other lectures, is a detector interferometer which will be in space, which itself is sensitive to much lower frequencies, from 10 to the -4 hertz to 1 hertz. Okay, so given the detector that you have in mind, what kind of distance measurements what kind of distances can you see to for binaries of mass m1 and m2? So that's what I'd like to try and answer right now. So to keep things simple, I want to focus on the in-spiral phase only. So here are two binaries, they're in-spiraling, getting closer and closer. At some stage they merge and then there's a ring down. To keep things simple, let's just focus on the in-spiral stage. And also let's initially neglect the expansion of the universe. And in fact, one of the things I want to argue to you is that that's not a good approximation. In fact, we can see binaries on very large distance scales. But let's neglect the expansion of the universe to start with. Now, from previous lectures, you've seen how the frequency of the gravitational wave during the in-spiral varies with, well, first the chirp mass. So the chirp mass I've written down here. And also varies with the time tau, time to coalescence, so tau, which is t minus tc. So that's, here in writing this formula down, as you've seen, there are a number of approximations which have gone in. So it's the dominant quadrupolar mode. It's calculated the lowest order in the Newtonian expansion. I'm neglecting spins, I'm neglecting tidal forces, and I'm assuming circular orbits. But it's good enough for the purposes of what I want to discuss. Okay, so this is the gravitational wave frequency as a function of time. In principle, it diverges at the coalescence time, but of course, in practice, this formula is not valid when the two objects merge. So how can we calculate a characteristic frequency at merger? Well, there's one way to do that. It's basically a dimensional analysis, if you want that. This is the only quantity you can build which has the correct dimensions, but you can also calculate a merger frequency by assuming that the merger occurs at the so-called innermost stable circular orbit, which it would be at a time slightly before the coalescence time. So how do you get that merger frequency? Well, essentially it comes from two things. So if you know the radius of the innermost stable circular stable orbit for a black hole of mass m, which is little m1 plus little m2. So it's something like 6gm. You also know that the frequency of the emitted gravitational wave is twice the orbital frequency of the object. And so if you use Kepler's laws, in fact, you can work out the merger frequency very, very straightforwardly. Okay, so what can you learn from this merger frequency? Well, you can substitute values for m1 and m2. So again, I remind you that capital M here is the total mass, m1 plus m2. So you can look at the typical merger frequency for a binary neutron star with typical masses of order 1.4 solar masses, or something of that order. And you get a merger frequency, which is in the LIGO or ET frequency band. So the LIGO frequency band is given in green here. So this is the sensitivity of LIGO as a function of frequency in green, or advanced LIGO in red. And for ET, its the sensitivity is in red dashed lines. So this is a relatively high frequency at the upper end of the frequency band. And if, of course, if you increase the mass, so if you look at stellar mass black holes of a mass of order 35 solar masses, then the merger frequency is of the order of 60 Hertz. So more or less right, slap bang in the middle. Of course, as the more you increase the mass, the lower the merger frequency. And so if you go to supermassive black holes, such as black holes the center of galaxies with a mass of order 10 to the 6 solar masses, then the merger frequency is of the order of the millihertz, which is exactly in the frequency band of LISA, which is shown here. So this is a frequency band of LISA and its characteristic sensitivity on the y-axis. So LISA will be sensitive to the merger of supermassive objects, and LIGO and ET to lighter objects, so neutron stars and black holes. Okay, another interesting quantity to bear in mind, or characteristic scale, is the merger time, or the time to merger, sorry. So we've now worked out when the objects, what frequency the objects will merge. So you can then say, okay, the objects enter my detector at some frequency f low, and then they'll merge at a frequency which we just calculated, right? The merger frequency. how long will the gravitational waves be observed by your detector? And that comes directly from the quadrupole formula. You just invert it essentially. Okay, you can, from here you can extract the time. So here I've written the time. And in this case, it depends on the chirp mass. Sorry, my notation has changed. The chirp mass here is cal m as opposed to mc, but it's the same thing. And then you can do a similar calculation. So if I have a binary neutron star which enters the LIGO detector at a frequency of about 20 hertz, let's say down here, and we've just worked out when it merges, then you can work out its duration, or how long it's observed. It'll be observed in the detector for about 4 minutes. You can do the same calculation for a binary neutron star, but this time entering the Einstein telescope detector window. And this, as I said before, is at a lower frequency, and you can see it down here, right? ET will be sensitive to lower frequencies. If you take a frequency of order 1 hertz, then the time to merge, or the time which this binary neutron star will be observed by ET, will be of order 5 days. Okay, now that has some interesting consequences, which I think will be very important in the future, which are the following. So Einstein telescope, as I think you've heard, is a future interferometer which will be on the ground, right? It'll actually be underneath the ground probably, but anyway, it's on Earth. And since ET will be observing objects which will be observed by the detector of order days, that means that you can't ignore the rotation of the Earth. Okay, the rotation of the Earth will be something you have to take into account when you're analyzing those detectors, because they're going to last, the events will last a few days in your detector, which is not the case for LIGO and Virgo, where the longest events only last for order a few minutes. So you can neglect the rotation of the Earth. So that's one thing which will be very important in the future when you want to extract cosmological parameters with ET. You have to include the rotation of the Earth in your analysis. And the other important consequence of this timescale of order of days is that so your detector will see this signal from a binary neutron star for of order 5 days, but that will very most likely be superimposed or overlapped by a number of other signals from other objects, such as binary black holes, because they merge on a much smaller timescale, which we'll see below. And given that we expect a lot of those events, over 5 days, there'll be a lot of overlap between different signals. So that makes, all I guess I wanted to say here is that data analysis, or the analysis or extraction of parameters from ET, will be a little bit more involved than the extraction of parameters with LIGO Virgo. Okay, let's carry on the timescales. So time to merger. Now let's take our stellar mass black holes with a mass of order 35 solar masses, entering the LIGO Virgo detector window at a frequency of about 20 hertz, and their signal has a duration of order, if you apply the formula above, of order 1.1 seconds. Good, and finally, let's go to LISA. So we saw that LISA could observe the merger of supermassive black holes. And if we apply the same argument, so exactly the same expression as before here, using a typical lower frequency for LISA, sorry, where's it gone? Here. Okay, of order, let's say 10 to the minus 4 hertz, then you can work out that that the supermassive black hole will be observed for a time of order 1 month before it merges. And that's precisely this red line here. This is a signal, typical signal for a binary black hole of mass 10 to the 6 solar masses, and which merges at a frequency of order 10 to the minus 3 hertz, and you can see it will be seen by the detector for a duration of order 1 month. And then let me do a last little exercise, which is to say, let's go back to stellar mass black holes. We've seen that they merge in the LIGO frequency band, but they can enter the LISA frequency band. Okay, they could actually also be seen by LISA with a lower amplitude, but they could be seen by LISA. And you can ask if stellar mass black hole enters the LISA detector window at some lower frequency of order 10 to the minus 2 Hertz, what's the duration of time between it entering the LISA frequency window and merging in the LIGO frequency window? And the answer is something of order 20 years. So in fact, there'll be events, which will be, I think, also important for cosmology, which will be observed in part by LISA, and then a number of years later will enter the LIGO frequency band where they'll be observed and where they'll merge. Okay. Right, so that's the time scales. How about the distance scales? So the distance or the amplitude of the in-spiral waveform you've seen in other lectures. So here it is. So it goes as the chirp mass to the 5 halves, and it's inversely proportional to the distance, which here I've called R not D. And it also, of course, depends on the frequency. And you can work out characteristic values of the amplitude. For example, if I take 2 stellar mass black holes at their merger frequency, so I replace F by the merger frequency here at the top, and I take a typical amplitude which can be seen by LIGO Virgo, h of order 10 to the minus 21, it gives me a corresponding distance of order 400 megaparsecs, which, if I assume a value of the Hubble constant, I can convert to redshift. I remind you that V is equal to, or CZ is equal to H0 times D, or H0 times R. So I can convert this to a redshift, and it gives a redshift of the order of 0.1. So we are looking at things on cosmological scales, okay? Because cosmological scales for me are whenever the redshift is of order 0.1 or more, if a fraction of something of order 0.1 or more, or even smaller, let's say. So let me try and put that in a slightly different way. So you can try and estimate to what redshifts a certain detector will be sensitive as a function of the mass, total mass of the binary system you're looking at. So the x-axis here is the total mass of your binary in units of solar masses. And the y-axis is the horizon in redshift to which you'll be able to see the object. So if you want, it's essentially a consequence of this formula, from which you've extracted the distance and converted it to redshift using a value of the Hubble constant. So there are lots of curves on here, but let's focus on 3. So let's focus on A+, which is advanced LIGO, which is in orange. And you can see that advanced LIGO will be sensitive to redshifts of order 1 or 2, okay, maybe 3. And its maximum sensitivity will be for objects of order 100 solar masses. And then it goes down again. Then the other curve, which I think is interesting, is the green one. So this is the horizon redshift for ET. So ET, as we saw previously here, is sensitive to lower frequencies, but it also has an order of magnitude at least better sensitivity, throughout the frequency range. So that means it can see further. And it can see further, so precisely how much is given by the green line. So the horizon or the redshift to which ET should be able to observe objects goes up to something of the order of 80 to 100 in redshift. So these are really huge cosmological distances. And they're really very exciting because in standard cosmology, before a redshift of 20, which is the dotted line here, in fact, structure formation tells you that you can't have any stars. It's it's the so-called dark ages before the birth of any stars. So if ET, when it's constructed, actually sees some binary black holes at these redshifts, and it's telling us that they can't be from standard structure formation, they must have another origin. And that origin could, for example, be primordial. So primordial black holes are formed, for example, during inflation, or as a result of inflation. And then finally, there's the red curve I wanted to show you, which is the horizon for LISA. Okay. LISA, as we've seen, is sensitive to the merger of heavier objects, and it will also be, it has a horizon which is even bigger in terms of redshifts. So the conclusion I wanted to draw from this part is that we're going to be interested in redshifts or distances which are huge, so large redshifts, which means that we can't neglect the expansion of the universe. So the previous expressions which were derived in Minkowski space are no longer true, or they have to be modified. And the second conclusion is that this plot is very nice, but to get it, I had to assume a value of the Hubble constant to convert a distance measured by from gravitational waves to a redshift. And that's precisely not the point of what we want to do. What we want to do is to use the data from gravitational waves to extract a value of the Hubble constant and not assume a value of the Hubble constant. Okay, so we have to change a bit our mentality in a minute. Okay, so the first conclusion is that we can't neglect the expansion of the universe. So how are our waveforms modified when our binaries are at cosmological distances? Okay, so let me turn on the expansion of the universe. So here's our same line element with scale factor A, which will be useful to write in terms of conformal time, so eta. And to get the waveform on cosmological scales, in fact, what we'll do is a simple, we'll try and do it in the simplest way possible. So what's the idea? So here's our source, okay, and in smallish distances and the local wave zone, so scales which are larger compared to the size of the source, but small relative to the horizon of the universe, we know the solution. We can neglect the expansion of the universe if we're sufficiently close to the source. So we want to take the waveforms that you've already seen in previous lectures, and then we want to essentially propagate them through the expanding universe all the way to the detector. Okay, or I've tried to draw this on a space-time diagram here, eta x on the left-hand side. So here's our source. The two blobs are the two objects in the binary, which are rotating. These are emitting gravitational waves which propagate along GD6, so light like GD6, to the observer. We know the waveform close to the source, and we now want to propagate it through the expanding universe to the observer. And so there are two effects that we have to take into account. Well, the first is time dilatation. So the time satisfies the standard expression, which comes from the fact that these go d eta at the source is the same as d eta at the observer, which gives the shifting of the frequencies between the observed frequency, the frequency of the gravitational wave at the observer relative to the emitted gravitational wave frequency at the source. And we'll have to take into account the fact that the amplitude of the gravitational wave will be decreased by the expansion of the universe. So let's try and do that. Just before I do that, let me mention that there's an important angle which is going to come into all this analysis, which again you've seen before, but let me stress it. If this is the source with its conserved angular momentum j, and our observer, so j is the vector in the z direction in this source frame, and our observer is at some point, some distant point, where they described by a unit vector n from the source to the observer, then the inclination is this angle between j, the unit vector j, and the unit vector n. And this inclination angle will be very important. Okay, so let's try and turn on the expansion. So there are a number of steps. So let's start off with the, as I said, with the waveform close to the source and the local wave zone of the source, which you've seen in previous lectures. So here are the two polarizations, the plus and the cross polarization, which depend on the inclination angle in a different way. So there's a factor of cos squared I in the plus polarization, a factor of cos I in the cross polarization. And I've written them as a function of the time measured by a clock at the source and as a function of the distance to the source. So we have the frequency of the gravitational wave as measured by a clock at the source and the phase in the source frame, which depends on the time to coalescence in the source frame. And as you've seen, and as we've already seen, in this source frame, where you can neglect the expansion universe, the quadrupole formula is the standard one, which I've written here, with cal n, the usual chirp mass, which you can integrate and hence find the phase here, the phase of the gravitational wave. Okay, so that's in the local wave zone of the source. And as I said, the next step is to go from the source to the observer, so to propagate those waves through an expanding universe. To do that, we need to know how those plus and cross polarization, so the two components of the perturbed gravitational wave metric, the perturbed metric in the transverse and traceless gauge. So what equation this satisfies in an expanding universe. So to do that, you have to take the perturbed metric, substitute it into the Einstein equations, and derive the corresponding equation for the perturbed metric H, which is here. So there's a second term with a second time derivative. There's a damping term from the expansion of the universe. There's the usual kinetic term. And then there's the source term, which it contains the transverse and traceless component of pi, or called pi, sorry. So pi itself is a transverse and traceless component of the perturbed stress energy tensor, which appears on the right-hand side of the Einstein equation. So the unperturbed stress energy tensor sources the background expansion A, and the transverse traceless part of the perturbed stress energy tensor sources the gravitational wave. So we want to understand how to propagate our Minkowski space solutions from the source to the observer. So we're away from the source. So in other words, we can turn off the source. We've already dealt with the generation of gravitational waves. Now we want to look at that propagation. So we turn this off. We go to conformal time eta, which I defined on the previous transparency, and we go to Fourier space. And we can write this equation in an equivalent way, where prime here is now a derivative with respect to conformal time. And the curly h here is the derivative of the scale factor, not with respect to time, but with respect to conformal time. And if the scale factor is a power law, well, it has a simple expression in terms of eta. And then you can solve this equation by doing a change of variable from h to q. So q is just h times the scale factor. It becomes an equation for a simple harmonic oscillator, essentially. So q double primed is k squared minus a squared, a double primed over a. And it turns out that if you work out a double primed over a for a power law scale factor, then this is essentially the Hubble parameter squared. And so then you can try and understand which term, so out of these two terms, which one is going to be the dominant one. So you can think about the scale. So k here is the equivalent of the wavelength of the gravitational wave. So we've been talking about frequencies which are of the order of a millihertz to a few hundred hertz. So you can work out the corresponding wavelength, which is not going to be huge. And that you should compare with the Hubble constant, so the size of the universe, or the inverse Hubble constant, so the characteristic length scale of the universe today, which is absolutely enormous, it's gigaparsecs. Okay, so in fact, for sub-Hubble modes, we're always dealing with sub-Hubble modes, so this term is a dominant term. We can totally neglect this one. And so then this just becomes a wave equation for Q. So Q double primed is equal to minus K squared Q with solutions of the form e to the I K eta. And then when you transform back to H, you have to divide by a factor of A. So in other words, for H, the amplitude is scales with 1 over A. So the solutions of our equation up here are plane waves with a redshifting amplitude. So now let's include that in our expressions for the plus and cross polarization. So we're taking the solution we had before and transform. We want to see what the new solution is at the observer. So first, let me include the factor of 1 over A from exactly what we found here, right? The factor of 1 over A from the redshifting of the amplitude. So here's the factor of 1 over A. And otherwise, I've done nothing. My expressions are still in terms of the time measured by the source clock, but we want to go to the observer's clock, TO. And they're still in terms of the frequency as measured by the source clock, but we want to transform it to the frequency as measured by the observer's clock. And we also have to deal with the phase, but the phase is actually simple to deal with because the phase by definition was the integral of the frequency. And if we change variable from the source clock to the frequency clock, well, you can, in principle, you should be able to see from here, f at the source clock times dt at the source clock, there's a factor of 1 plus z divided by 1 plus z, so they cancel. So it's actually exactly the same thing at the observer's clock. Okay, so this last term is easy to write down at the observer. So now we just have to do this change of variables to write the frequency of the source in terms of the frequency of the observer. So let's do that. So here was our previous expression. So going from the first line to the second line, I'm replacing the phase at the source by the phase of the observer. We saw it was the same. And I'm also replacing the frequency at the source by the frequency of the observer, where there's a factor of 1 plus z, which I have to add. So now this is in terms of the time at the observer. Now let me take this factor of 1 plus z, which comes to a power 2/3, and stick part of it in the factor of gm and the remainder in the denominator. So there's a factor of 1 plus z to the 5/3 divided by 1 plus z. So I get back the 1 plus z to the 2/3. And now let me rewrite this in terms of a redshifted chirp mass. I'm going to absorb the factor of 1 plus z into the mass and absorb the factor of 1 plus z into the denominator into the luminosity distance. So in other words, my waveform at the observer is expressed in terms of a redshifted mass, also known as a detector frame mass, and the distance dl, which is in fact nothing other than the luminosity distance. And I can re-express it in terms of cosmological parameters, the ones precisely which we're after. In fact, you can show that the expression for dl is given exactly by what I've written here. So it contains the Hubble constant, omega m, and omega lambda. Okay, the final thing I want to stress, I've rewritten these same expressions. I dropped the O, the index O for the observer, and I'm just labeling it T now. The final thing I want to stress is that the phase at the observer, if you take the previous expressions and you replace the frequency at the source with the frequency of the observer, the quadruple formula, blah, 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 you do a few calculations, you find that the frequency of the observer also depends on the redshifted chirp mass. Okay, there's some approximations that you have to make for that to be true, but essentially the phase at the observer also depends on the redshifted chirp mass. So let me try and summarize this. So the summary is that if you include the expansion of the universe, the phase depends on the redshifted chirp mass, and the amplitude of the wave depends on the combination of the redshifted chirp mass and the luminosity distance. So what does that tell you? So I think it's very important to understand the consequences of that. So when you observe a gravitational wave signal, you observe a wave, right? And from the oscillations, you can try and extract the frequency. And what we've just said is that the frequency depends only on the redshifted chirp mass. In other words, if you think about it, it depends not on the absolute value of the redshift, nor the absolute value of the chirp mass. It just depends on this combination. So you could have, for example, a very light, small chirp mass at very high redshift, or a very high, or very small mass, sorry, a very small mass at very high redshift, or very large mass at low redshift. They would have the same chirp mass, but the gravitational wave information would not be able, you would not be able to distinguish between these two cases. So in other words, from the phase information, you can't extract the redshift unless you know for some reason some information on the source frame masses. And again, that will be extremely important in what follows. Okay. So the redshift, sorry, the phase information cannot tell you anything about the redshift. And similarly, the amplitude information cannot, for exactly the same reason, it can't tell you anything about the redshift either. It can't be used to extract the redshift because it only depends on a combination of redshift and co-moving distance, if you want. So in other words, there's a perfect degeneracy between source masses, redshifts, in fact, spins in general. And so gravitational wave information, using observations of gravitational waves, at least purely gravitational information, you cannot in any way extract the redshift of your sources. So you need to find some other way. Okay, let me say that in another way. So we saw previously that the redshift is related on small scales to the Hubble constant and the distance d. Here we have a way of estimating the distance, but we have no way of estimating the luminosity distance, of estimating the redshift. Okay, so we need some extra non-gravitational information to extract the redshift. Okay, so let's just think a little bit more about the amplitude. So we said the amplitude of the gravitational waves depends on the luminosity distance, and this is its expression. So here I've drawn the luminosity distance, plotted the luminosity distance as a function of redshift, and I've played around with the value of omega m, and I've played around with the equation of state of dark energy. So you can see that how the luminosity distance varies with z depends on these parameters. Now, the LIGO-Virgo detectors, as we've seen, are sensitive to redshifts typically of order of 0.1, let's say to of maximum 0.1, of redshifts of order of maximum 0.1. In other words, we're looking at very small z. If you take this expression for very small z, and you Taylor expand it, essentially, you can show that it reduces to the Hubble law. Okay, so dl is cz over h0. So with LIGO and Virgo, we can probe only the very small corner down here of these curves, where they all essentially overlap, and the gradient will be given by 1 over h0. With ET and LISA, as we've also seen, we can go to larger redshifts, and then dl will depend on the other parameters, so not only h0, but also omega m, omega lambda, and the equation of state of dark energy. So in principle, we can access other cosmological parameters than h0. Okay, so essentially doing cosmology with gravitational waves boils down to measuring the luminosity distance, dl, with the signal, and also determining the accuracy with which you can measure dl, and determining the redshift with some accuracy. Okay, so that's what it boils down to. What's the time now? 11:12. I suggest we have a 5-minute pause, if that's okay with everyone.
Yeah, it's 11.
Unless there are any questions, which I'm happy to take during the pause.
Maybe I have one. If you can go back one slide.
This one? No.
No, go back.
Yep. Sorry, what's it?
Sorry.
Yeah.
Yes, this one. So what you're saying here is based on the leading order in the post-Newtonian expansion.
Mm-hmm.
But I guess there are more information than that if you go beyond the leading order.
So the conclusion, the bottom line conclusion is actually true. If you have black holes, for example, if there's no matter, I mean, if they're not neutron stars and there's other physics involved, if there's only gravitational physics involved, it'll be true to any order that you can't extract the redshift.
Okay.
And that's just basically because gravity is you can do a scale transformation, okay, and gravity is scale free. Which is a pretty fundamental result. So the trick will be to extract the redshift will be either to use some kind of non-gravitational information, something about the mass. For example, if you know something about the source frame mass, then given that you observe the redshifted chirp mass, it can tell you something about the redshift. Or if you have binary neutron stars, then indeed to higher order, you have contributions that come really from the you have contributions in the waveform which come from the internal structure of the neutron star. Does that answer your question?
Yeah.
Okay, so let's take a 5-minute pause.
Okay, are there any other questions before taking the pause? Okay, so shall we reconvene at 11:20?
Yep.
Is it fine?
Sure.
Okay. Okay, shall we start?
Yep. Okay, so we've arrived at the point that with gravitational wave observations, we can determine DL, but we need extra information, non-gravitational information to extract the redshift. And at least on small, for small redshifts, this is a link between redshift H0 and DL. So if we want to, the error, and essentially the error on the H0 will depend on the error on Z, which we already mentioned. So we need the redshift with some accuracy delta Z. And from the DL, it's important to know the error on the distance measurement. So the next two questions I want to address is, what's the accuracy of the gravitational wave measurement of the luminosity distance? And how can one determine the redshift, and with what accuracy? Because both of those will in turn impact the accuracy of the measurement of the Hubble constant. So let's start with the luminosity distance measurement and its accuracy. Okay, so here's the measurement of the Hubble parameter with GW 170817, which I showed you before. And in fact, there's a large error, contribution to the error from the error of the distance on the distance. So this is the posterior on the measurement of the distance from GW 170817. And you can see that this is not exactly peaked around something of order 40 megaparsecs. It's extremely broad, this distance error. And I now want to try and explain to you why it's relatively broad. Okay, so here's our binary system at an inclination I to us. And here's a very modern detector. And so in an ideal world, what would our detector measure? So in an ideal world, one would measure the two polarizations of the gravitational wave separately. So H plus and H cross, we would measure them separately. From the phase information, as we discussed, we would extract the redshifted chirp mass. then if we know the two phases separately, we would divide one by the other. So that would cancel out all the factors of m here, of d, etc. All of these, the first factor would cancel out. We know the phase, so we would then, from the ratio, we would extract the inclination angle. And once you have the inclination angle and the phase, we would then extract, since the phase depends on the chirp mass, we would then extract from any one of these the luminosity distance. But that's an ideal world, and it's not the reality of gravitational wave interferometers, because what a gravitational wave interferometer measures, so here I've labeled the interferometers by an index A, because there's more than one. For example, for LIGO, Virgo, there are 3. So what does the gravitational wave interferometer measure? It actually measures a linear superposition of H plus and H cross. And the linear superposition is weighted by these, what are known as the antenna pattern functions, which I'm sure you've seen before, which depend on a number of things, including the geometry of the detector, so its opening angle of the two arms. It depends on the position of the source on the sky, so alpha and delta are the declination and right ascension, so the position, angular position of the source on the sky. And it depends on also the polarization angle, which I'm not going to mention here. And as we've seen for LIGO and Virgo, at least, we can ignore the time dependence of these antenna pattern functions, because all the signals that we see with LIGO and Virgo are short compared to the rotation, or the rotation of the Earth. They're short on the timescale of a day. But with ET, we wouldn't be able to do that. So in reality, the gravitational wave detector measures not each individual polarization, but a sum of the two, weighted by these so-called antenna pattern functions. And you can plot those pattern functions as a function of alpha and delta, so on the sky. In fact, I'm going to show you the sum of the squares. It gives you an idea of what's going on. So here's the sum of the squares. So the antenna pattern function at Virgo on the left-hand side, and the antenna pattern function at Hanford on the right-hand side, so on the celestial sphere. And the big black dot here is the position on the sky of GW 170817. And so what you can see is that for Virgo, it's, as you've probably heard before, it's in a so-called blind spot. It's where the antenna pattern functions are very small, whereas it was in a nice red patch so where the antenna pattern functions are of order 1 for Hanford and Livingston. So in reality, the gravitational wave detector measures a superposition of those polarizations. And you can ask yourself, what are the typical distance errors? And how do they depend on the position of the source on the sky? So for example, here, this event was in a position where the antenna pattern functions are small for Virgo. If we'd considered an event where the antenna pattern function was high in Virgo and high in Hanford, would one have a smaller distance estimation of the distance error? Okay, so those are the questions we can ask. And we can try and give an outline to the answer of that question. So let me try and do that for you. So let's transform from real space to Fourier space. So here's the amplitude as measured by the detector in Fourier space. I've dropped the label A now for simplicity. So the waveform in Fourier space has a phase and it has an amplitude. The details of the phase are not particularly important, but what's important is that it depends on the chirp mass, as we've already seen. And the amplitude depends through the f's of the position of the source on the sky. It goes as 1 over the distance, and it depends on the chirp mass, as we've already seen. And with those, we can try and estimate the error on the distance. And the way we can do it is a quick and cheerful method. So it's a so-called Fisher matrix approach. And I'd like to outline how that works very briefly. Okay, so how can we estimate the error on the distance? So the the procedure is the following. So what the detector actually measures is a signal, which is the sum of a part which comes from the noise in your detector plus your signal. So the gravitational wave part, so that, sorry, the signal was not the, S was not the right, really good letter, but never mind. So what the detector sees is noise plus the signal coming from the gravitational wave, so H, which depends on parameters including the distance, okay, luminosity distance. And then it turns out that if your noise in your detector is Gaussian and stationary, then there's a natural inner product which you can define, which I've written here, in terms of the waveform in Fourier space. So that was on the previous slide down here. And using this scalar product, you can define the Fisher information matrix, which is the same scalar product, but in terms of the derivative of the waveform with respect to the parameter of your interest. So what are the parameters which interest us? There's the amplitude of the waveform, so A, here. And the second one is the chirp mass. Once you have this matrix, you can invert it and work out its diagonal elements. And the square root of those diagonal elements give you an estimate of the error on your parameter theta I. So we can do that calculation for H, which was the same H as before. We can work out its derivative with respect to the amplitude, for example. So H is linear in A, so if I differentiate A with respect to A, then it drops out. If I differentiate with respect to log A, I get H back again. And you can also calculate its derivative with respect to the chirp mass, which I've written here. If I substitute this derivative with respect to log A into here, you can see that what I'm left with is actually the scalar product of H with itself, which defines the signal to noise ratio. So you can see that from there, hopefully, what I've written here, that the error in the amplitude, so this was before we had log A, but if we transform it into A, the error of the amplitude, relative error on the amplitude, essentially goes as 1 over the signal to noise ratio, so how loud your signal is in your detector. And I've normalized it to take out a factor of 10 in the signal to noise ratio. Whereas the error on the chirp mass is much smaller. It's of order 10 to the minus 5 times the similar factor of rho, so 10 over rho, times the chirp mass in units of the solar mass. So in other words, for a given signal to noise ratio, the error on the chirp mass is generally much smaller, this factor of 10 to the minus 5, than the error on the amplitude. And since the amplitude is related to the distance, it's therefore much smaller than the error on the distance. And you can see, or you can guess at least, that from here, the error on the distance is typically of order 0.1. But that doesn't answer one question. So the amplitude here depends on 1 over the distance, but it also depends on the position of the source on the sky, alpha and delta. So then you can ask yourself the question, are there any kind of golden spots in the sky for which the error on the distance would be smaller because of these antenna pattern functions? You can also ask yourself, can I go beyond this Gaussian approximation, which is actually not very good for the distance because its posterior is anything but Gaussian? And also, how does my error depend on the number of detectors I have? And so you'd have guessed the more detectors you have looking at the same event, the smaller the errors in the distance would be. And all of these questions you can try and answer. And so this plot looks complicated, but there's a clear message which I want you to take away from it. So this plot shows 4 cases. So it shows, so for each of the 4 cases is the following. So the first one is a detector network consisting of Hanford and Livingston detectors only. The second one has Hanford, Livingston, and Virgo. The third one adds to that network the Cagra detector. And the fourth one adds the detector and future detector in India. And the color scheme is a geometrical quantity that you can calculate that turns out to be directly related to the error in the distance error. And it turns out that the more this geometrical quantity epsilon is large, the less good control you have on your distance error. And so the spots where epsilon is red are spots where you can't measure the distance very accurately, whereas where it's blue, you can measure it slightly more accurately. So the first message is that the more detectors you have covering larger area of the sky, the more you have blue spots. So the more you have control on your distance error. And the second message that comes out of these plots is that the error on the distance, which you can't see very well because it's in these are lines of iso distance error, if you wish. So the distance error is largest where this value of epsilon is big, but the value doesn't change very much. It changes from a fractional error of something like 20% at worst to 12% at best. Okay, the worst number actually decreases as you increase the number of detectors, but generally the distance error does depend with position on the sky, but it's not very sensitive to the position on the sky, nor on the number of detectors, because it varies between something like 10 to 20%. So in other words, there are no particular positions on the sky where you would reduce that distance error. It's always going to be of order something like 10 to 20%. And that's simply because of the degeneracy with the inclination angle, which you can't get rid of. Okay, let's just focus on the right-hand plot here. This shows the 10 black hole events seen in the first LIGO-Virgo catalog. And it basically shows in reality what I said to you theoretically, that the error on the mass increases as the mass increases, which was here. Okay, the larger the mass, the larger the error. Okay, and that the error on the distance is always very big. Okay, of order 10%. Okay, so in order to measure cosmological parameters accurately, you want to reduce the error on the luminosity distance as much as possible. So how could you go about trying to do that? Well, one way which we haven't mentioned at all so far is to consider the effect of spins. So far I've turned off the spin completely, but if you add spins, if you have spinning objects, then there's possibly a way of reducing your error on the distance measurement. And that's the following. So if you have an object which has spin 1, so S1 for the first spin, and a spin S2 for the second spin, and you calculate the total spin capital S, so S1 plus S2. And if it's not aligned with the total orbital angular momentum L, then you can show that these vectors are actually going to precess around a common J, which is the sum of L plus S. And the effect of that is that this precession is that the detected radiation has a time-varying polarization. And it turns out that, again, another consequence is the inclination angle, which here is called theta LS, will vary with respect to time. And so that adds another phase modulation of the gravitational wave signal, which you can try and detect. And this plot, I think, is very interesting. It's from a paper by Vitale and collaborators. And it shows the distance error, fractional distance error, as a function of the inclination angle for a system consisting of a binary neutron star, well, a neutron star, sorry, on one hand, and a black hole on the other hand. So the neutron star was always assumed to have 0 spin, and then they've played around with the spin of the black hole. So the black hole can have a spin, actually spins of 0.5 in the green curves, and spins of 0.89 in the blue curves. And what changes between the different curves is the angle tau, which is the spin of the black hole relative to the spin of the of the total orbital angular momentum L. So if tau is equal to 0, the spin is aligned with the orbital angular momentum and there's no precession. And that gives you the solid lines. There's no precession. And you see how the distance error is of order, well, as we said, right? Somewhere between 10 and 100, well, 100 here. And if you let the black hole have a spin, so tau is non-zero, you see that the error on the distance is much smaller because of the effects of precession. So the conclusion of this paper is that if you can see systems or detect systems which have spin, you can reduce the error on the distance, which I think is very interesting. And there's another way in which you can hope to reduce the error on the distance, and that's by detecting these what are known as higher order modes. So far we've discussed only the dominant quadrupolar mode of gravitational waves, so the H22 mode. But as I think you probably heard in the lectures by Luc Blanchet, in principle there are other modes, because this combination of plus and cross is generally decomposed into spherical harmonics with coefficients HLM. And the dominant mode is the 2-2 mode, but there are higher modes which depend generally on the mass difference, delta, which is here, and scale differently with inclination. So if you have two masses which are very different, so M1 very different from M2, you can get these higher order modes which become more important, though they're still, as you can see from this plot, they're still really much smaller, an order of magnitude smaller than the dominant 2-2 mode, quadrupolar mode. But if you can measure them, and given that they scale differently with the inclination, you can also try and reduce the error on the distance. And I think this is shown extremely well in this plot, which is for the gravitational wave event GW 1904-12. So this shows the posterior on the luminosity distance and on the inclination, as measured if you just from the dominant multiple, so from the 2-2 multiple, and here it's projected out onto distance here on the right-hand side. Okay, so this is the error on the distance, and you can see that it's very broad, it's large. If you include the effect or the observation of higher multiples, then that's the red dashed line. You see it reduces the error on the distance. And if on top of it, you take into account precession and higher order multiples, you see that the posterior on the distance is much more peaked and has a smaller width. So you really do reduce the errors on the distance. So those are some keys to getting the error, reducing the error on the distance measurement. Okay, as I said, then the last crucial point is how do I measure the redshift of my source? Because I need the redshift in order to determine cosmological parameters. And here there are a number of different possibilities. And I'm mainly going to, in fact, focus on the third, which I think is a new direction which this field is taking, but I do want to go through the first two as well. So ways of measuring the redshift. So the first would be to see a direct electromagnetic counterpart of your gravitational wave signal. So from the electromagnetic counterpart, you can determine the redshift. That's the first method. A second method is to use galaxy catalogs. So if you have galaxy catalogs, you can determine which are the galaxies within the localization region of your gravitational wave signal. And that you can use from the redshift of the galaxies in your catalog, you can try and use to extract the redshift of your gravitational wave event. And then there's this third, I think, very interesting way of going about things, which is to put knowledge in, to assume you have knowledge on your source frame mass. And that's something which I'll stress a lot more in 5 minutes time. Okay, so let's go to the first one. So direct electromagnetic counterpart. So that's something that that one should have in the case of the coalescence of two neutron stars or a neutron star together with a black hole. There's a lot of physics going on in the coalescence, which is summarized in this picture here. What happens when two neutron stars or a neutron star and a black hole merge. So there's a gravitational, so there's a burst, a GRB burst, a gamma ray burst. And then there's these kilonova, which again, other people have told you about. So I'm not going to go into the details of that. But that was precisely what was observed for the neutron star, binary neutron star GW 170817. So with the counterpart, with the electromagnetic counterparts, it was possible to measure the redshift of the source, which was identified with a particular host galaxy, this one here. And it was from the redshift and its errors, which somebody already mentioned, that you could determine the posterior and Hubble constant, which I've already shown you. It's the orange curve. Yeah. Okay. So there's an error precisely in the redshift that we mentioned, caused by peculiar velocities. There's the error in the distance, which was large, and which is a dominant error in here. And of course, there are other instrumental uncertainties. Okay, so with an electromagnetic counterpart, you can, in principle, measure the redshift. The problem is that so far we've only had one of those, GW 17817. There's been no other binary neutron star mergers so far in LIGO and Virgo with an electromagnetic counterpart. So this method is slightly blocked. I mean, we haven't made any progress since then on the measurement of the Hubble constant with this method. So we need other methods to determine the redshift, which are not based on having an electromagnetic counterpart to the event, and which would work, for example, for black hole binaries, which have no electromagnetic counterpart. And that is, one of them is to measure the redshift from all the galaxies, as I said, which are localized in the gravitational wave localization volume. So if your gravitational wave event is sufficiently well localized in the sky, and if you have galaxy catalogs, then you can infer Z by identifying all the hosts in your localization region, incorporating the redshift of each of these hosts, each of these dots. And then if there are enough of them, then you can, in fact, by average, the error in which galaxy is the correct one will average out. Now, this method has been applied to the binary black holes which were observed in the O2 observing run of LIGO and Virgo. Now, it's complicated. It's a complicated method, I think, because, and not entirely satisfactory in my mind, because, well, there are a number of problems or difficulties you have to overcome at least. Firstly, not all events are well localized in the sky, so they cover different regions of the sky. Then not all the galaxy catalogs will cover the whole localization volume that your gravitational wave observation points to you to. And further, the galaxy catalogs may not be complete. So this is all information you have to fold in if you want to use galaxy catalogs to extract the redshift. So here's an example of what I'm talking about. So here is the localization on the sky of the different events in the O2 catalog. Some of them are well localized, such as this one, GW 170817. And there's another one here which is well localized, GW 170814. But the others typically cover big patches of the sky and possibly multiple patches of the sky if they're only seen in one or two detectors. And then you need to use the galaxy catalogs. Galaxy catalogs have to exist which cover those regions of the sky. Now it turns out that there's one of these gravitational wave events, GW 170814, down here, which was well localized and is very much within the galaxy, the region studied by the galaxy or examined by the DES catalog, Dark Energy Survey. And it turns out that there was something like 31,000 galaxies in that catalogue which cover the region of the sky of GW 170814. So with that particular event, one can try and extract the redshift, and in fact from the others as well. Putting a long story short, if you take GW 170817 with only the value of the Hubble constant we've seen many times is this one, if you include the 6 black holes with the sufficient SNR in the O2 observing run of LIGO and Virgo, it leads to a very small, well, a 4% improvement on the measurement of H0. So there's information, but it's not, I mean, it only leads to a marginal improvement. So that's in fact the blue curve here. The information you get on the Hubble constant from only the black holes is in orange. Okay. Now, so far we've talked about of order a few events, right? One or 6. You can ask yourself the question, what will happen if I have more events? And what are the prospects for solving the H0 Hubble constant tension with methods 1 and 2 if I have more events? And this, I think, is summarized on this plot. The x-axis is the number of events. The y-axis is the fractional error on the Hubble constant. And the different colors correspond to different scenarios. So the one in this kind of pink color assumes that you have a counterpart. So you know the host. So it's the equivalent of method 1. And you can see that the error on H0 decreases like 1 over the square root of n. So the more events you have, the smaller your errors will be on the Hubble constant, as you would expect. If you have galaxy catalogues and the errors are larger, they still eventually decrease as 1 over square root of n, but you can see that depending on how complete your galaxy catalogues are, the errors will be, well, the less complete your catalogue, the larger the errors. And I think an example is here, that if you want the Hubble constant to an accuracy of 3%, so this is here, 1, 2, 3, then you would need 30 events with an identified host galaxy, or 100 events with a, sorry, that's a mistake. With a galaxy catalogue that's 100% complete.
Sorry, Danny, there's a question.
Yeah.
Why should there be less than 12 SMR to get the 4% improvement for your?
It should be greater than. Yeah, okay. So if you look at this column here, so the SNR is a measure of how strong your signal is relative to the noise in your detector. And to have a detection, there's a threshold on the SNR, which is generally imposed. And in this particular paper, the threshold imposed was that the signal to noise ratio should be larger than 12. And so that, if you look on this column, it actually excludes the number of the events. It excludes this one, and these last 2. Okay, so that's why there are, in fact, only 6 black holes left. Does that answer the question?
Yes.
Any other questions? No? Okay. Right, so in the last 10 minutes, I want to go on to point 3, which I think is going to be the way to go in the future. Because, well, at least I think the using galaxy catalogues for ET and for LISA probably won't be a viable method, because as we saw, they can see up to such large redshifts that the galaxy catalogues probably will just not be complete at those redshifts. So I'm not sure that this will be a very efficient way of approaching the problem of measuring the redshift. And the other advantage of this third idea, so to use some knowledge of the source frame mass distribution, is that it doesn't depend on any electromagnetic data, so it will also work for binary black holes. And that's furthermore an advantage because binary black holes are heavier, and as we saw, they can be seen for larger Z. And there are in fact more of them. So as we've seen, the more the events, the lower the errors. And here we have a method to determine the redshift that should work without an electromagnetic counterpart. So what's the basic idea of this third method? So as we've seen, what a gravitational wave, what you measure with gravitational waves is the redshifted chirp mass, or what I've called the detected masses M1 and M2. So detected means redshifted, which is related to the source frame masses, what I previously called little m1 and m2 without the source, but here I really want to stress what the parameters are. So they're the masses at the source and the masses at the detector. You measure the masses at the detector, which are related to the masses of the source by z. And z itself is a function of the luminosity distance of h0, etc. So if you have information on the mass of the source, given that you measure the mass in the detector frame, you therefore have some information on the redshift. So in other words, from knowledge of the source mass, which could be one or many sources, if you have many black holes, you can get some information on the luminosity, on Z, on the redshift. And the more sources you have, the smaller you expect the errors to be. So what kind of knowledge can one use on the source frame masses? So here I've tried to draw a schematic plot of the knowledge that one might have on the source frame masses. So this is the distribution in mass. I've just taken the mass M1. So what do we know? So from general relativity and known nuclear physics, we think the neutron stars have a maximum mass. Okay, maximum mass of order, I don't remember the exact number, something like 2 point something solar masses. Then standard physics seems to say, or stellar physics seems to say that then there's a gap between the most massive neutron star and the lightest stellar mass black hole. So there's the lightest stellar mass black hole allowed by stellar evolution. And then there's a distribution of masses up to another maximum mass of stellar mass black holes. And then beyond that, so this is another meant to be a mass gap where there are no black holes. Beyond that, there are intermediate mass black holes. In other words, this masses of black holes, there's some information that we know on source frame masses, in particular that there are some scales in the problem. So the maximum mass of a neutron star or the minimum mass of a black hole, which we can use to feed into information on the source frame mass. And in fact, what is the mass of the stellar mass black holes has been determined to some degree by the LIGO-Virgo collaboration, and with the O3 RON. And what's observed is a mass spectrum with a peak around 35 solar masses here, a decrease beyond 60 solar masses here, and a cutoff, a lower mass cutoff at 8 solar masses down here. So with this information coupled, we can try and extract the Hubble parameter. In fact, one should do the analysis at the same time, right? Extract these lower and upper masses at the same time as we want to extract the Hubble parameter. And so before I show you some projected calculations that use that information, let me just go back to the event rate. As I said, the more events you have, the smaller the errors will be. And as we've seen, Einstein telescope and LISA will see to very much larger redshifts. And at least for ET, you can estimate, given the rates of events that you've seen in LIGO and Virgo, you can actually estimate the number of black hole events that you'll have, the number of neutron star events that you'll have, and also the number of neutron star black hole events that you'll have. And the numbers are huge, okay? Of order 10 to the 5 to 10 to the 6 binary black hole events per year. then you'll also expect binary neutron star events with about 10 to the 4 per year, of which maybe some 10 to the 2, 10 to the 3 will have counterparts, electromagnetic counterparts. So there are many events, and if we know something about the mass distribution of those events, we can extract H0, as I'm going to show you. But I should say that unfortunately, when you go to these redshifts, there's another source of error in the distance measurement that one should include, and that's an error in the distance coming from the weak lensing of gravitational waves. And unfortunately, this becomes another source of error, which is important at large redshifts, at these large redshifts that can be seen by ET. Okay, so ET will see a number of events. So here I'm focusing again on the number of events which the Einstein telescope should be able to see as a function of the mass of those events. So ET is in green, the number of events as a function of mass. So we're really talking big numbers here, right? Of order 10 to the 3. And it's quite interesting to compare them to the O2 run of LIGO, right? The numbers are much smaller down here. Let's skip the right-hand side. Okay, so how can you forecast what cosmological, your errors on the cosmological parameters using information on the mass models? So how can you do that? So many people have done it, and I've put a list of references here. So generally what you do is since ET is not running so far, you have to proceed through the construction of mock catalogs. So fake catalogs of gravitational wave signals. So you distribute your events in redshift. You use fiducial values of the Hubble parameter and other parameters to determine from their redshift the distance. And you make some assumptions on the errors on the distance of your events in your catalog, either using the Fisher matrix approach that we've already mentioned or more advanced methods. Then you calculate the signal to noise ratio for each of the gravitational wave events in your catalogs, and you keep it if it's bigger than some threshold, such as 12, as we already saw. So then you have a set of observable events in your fake universe, if you want, to which you add information on your mass model. So you draw masses from some probability distribution. So all your events, you give them some mass. So mass for each of the pair of objects in your binary. So you choose it from your mass model. And if you're talking about neutron stars, or maybe neutron star black hole binaries, you also need a criterion to determine which of those events will be observable in electromagnetic waves.
Annie?
Yeah.
I have a question.
Yeah.
So I guess that there will be parameters in this mass model.
Mm-hmm.
What are they?
Okay, so what are they? Good, here they are.
Oh.
Okay, so the parameters, so this is an example of a simulated model population of binary black holes in Einstein telescope. So this is how the binary black holes are distributed in distance, okay, which corresponds to a redshift between 0 and 10. And the maximum around 1.5. And then your question is, what about the mass distribution? Okay, so what's assumed is that in the source frame, so the source frame, this is the probability distribution in the source frame, they're focusing on stellar mass black holes, which is this curve, okay? They give it a shape which they don't know. They characterize it by a power law with a peak, and they leave those as free parameters. But what they do is that they fix the lower mass and they fix the upper mass of the distribution of black holes in the source frame. So the lower mass comes from so the lower mass is the physics, if you want, well, it's gravitational physics. I mean, can you have a black hole of a mass smaller than 5 solar masses? Assuming no, then they fix this value. And they fix the upper value to be 60s. The source frame masses are the ones which are not, which are these two, right? The blue and the orange one. And then from there, you can determine, given that you know the distance distribution, you can determine the distribution of those objects in the observed source frame mass, okay, multiplied by a factor of 1 plus z. So that's the blue and orange ones. And from there, they try and extract the Hubble constant. And in fact, they also extract omega m. So Filippo, did I answer your question?
Yes, so if I understand correctly, apart from fixing the minimum and maximum max, where physical input enters, the rest is the phenomenological.
Right, which they marginalize over.
Yeah, okay.
Okay.
I see.
So their results are summarized in this in these plots, where they assumed 1,000 gravitational wave events measured by ET. And they showed this, so these are the joint posteriors on H0 and on omega m. And there are two curves here. So they're the ones in blue, and they're the ones in orange. So the ones in orange assume that all the information about the population parameters is known. So this exact shape of this distribution is known. So the slope, the height of the Gaussian peak, and its position. And what you find is obviously that the errors on the Hubble parameter are extremely small. Okay. In the blue curves, they assume that they don't know anything about the population parameters apart from n min, the minimum mass, okay, of 5 solar masses, and the maximum mass of 60 solar masses. And they marginalize over the population parameters, which leads to larger errors on the Hubble constant on an omega m, as you can see here. But the conclusion of that paper is with 1 year of observation in ET, should be possible to constrain the Hubble parameter to a few %, given the current knowledge on the black hole mass distribution. So I was going to give further examples of that, but unfortunately we're running out of time. So let me jump to the conclusion, if that's okay with everyone.
Yeah, well, actually you have, in principle you have until at past.
Oh, I thought it was 2 hours, but I'm happy to.
Yeah, you have half an hour more. Unless there are questions, of course, you're invited to ask questions.
Are there questions?
Okay, maybe I have one.
Yep.
So here, like, again, about these two parameters, like that are astrophysically motivated. If you have, how the analysis would change if you have, for instance, I don't know, a black hole below that in the mass gap or in one of the two mass gaps, for instance.
Yeah, right. So, okay. So there, I think, let me try and answer that question. So your question is, if you observe a black hole in those mass gaps, is that what you're saying?
Yeah, because here, I mean, my humble understanding is that you assume the mass distribution in first place in the source frame.
Right.
Then you observe, I guess, the mass distribution in once you collect all the detections, and from that you infer the distance, right? The probability distance.
And the Hubble constant. Sorry.
Yeah, and then the Hubble constant.
So that's precisely if you see an event which is in the mass gap, if you observe an event in the mass gap, that will tell you something about the Hubble constant, right?
Mm-hmm.
Do you understand that?
In the sense that you have to if you observe something in the mass gap, you have to sort of do the analysis with this minimum mass.
No, so you have to understand that the information is put in the source frame, okay? So if in the source frame you say that I can't have a black hole of a smaller than 5. So let's say that in the source frame I say I can't have a black hole of a mass lower than 5 solar masses, okay? Then you observe a black hole of 4 solar masses. Then that would tell you something about the Hubble constant, right?
Yes.
So that's precisely how you want to use that information. Because the only way that you would be able to observe a black hole in that mass gap is if the Hubble constant is sufficiently, well, that's a bad example, if it was sufficiently small, right? So precisely the observation will tell you something about the Hubble constant. And that's exactly the information one wants to use.
Okay. So let's say, then I don't want to bother too much, but just to be, let's say there is not degeneracy in the sense that, for instance, if you have something in the mass gap, then it would translate in mass distribution in the detector frame, let's say, that gives you like a probability distance. Okay, maybe I'm not clear here. What I want to say is that you assume in this analysis, if I understood correctly, that there is a minimum.
Oh, I can't hear you anymore.
Sorry?
I didn't hear you. Sorry. Say that again.
So there is a minimum mass in the primordial.
Yeah. So let's look at this plot again. Okay. So the orange and blue squares right here, it's a distribution in the source mass frame. Okay. Which goes from 5 to 60, and the full ones here are the distribution in the detector frame, the detector frame. Mm-hmm. Okay, so your question is?
Okay, so my question is like what we observe is the one in the detector frame. Obviously.
Yeah, these, right? Yeah.
And then given our assumption on what is in the source frame, we infer the probability, the distribution probability of the distance, and therefore the Hubble the Hubble parameter. So now, if you have something in your, if you detect something that would look like if it was in the mass gap, it can sort of be smeared by the value of the Hubble constant that you infer. In the sense that you just change the probability on the distance of this mass distribution.
So I'm not sure I understood your question now.
Okay, maybe you just go ahead. I try to reformulate better the question and I ask at the end. Sorry.
Michele?
Yeah, sorry. Hi, thank you, Filippo.
Ciao.
Hi, Danièle. Well, I just have a brief comment before the question about the question by Jacopo. Maybe he just meant that if you observe something in the mass gap, of course, the value of the minimum or maximum mass of your mass model and H naught are degenerate. I mean, can be degenerate, but to infer H naught, I guess you marginalize over the values of the mass function. I don't know if maybe that is the direction of the question. But okay, maybe we can discuss this later. And having said this, can I ask my question?
Sure.
If it's not too late. So I had two small actually. One is about the error on the lensing that you meant, the lensing error on the L that you mentioned a couple of slides before. I remember that error was like a rough estimate of some old paper, but then someone like in the group of Matarrese did the actual calculation and they showed that actually that error is very small, at least for ET. I don't know if that...
So I agree with you. There are different estimates around.
Okay.
And it seems to me that there's still an open subject, to be honest.
Okay.
Yeah.
Okay, then maybe we can discuss this in another. Okay, thank you. And the other small question about this you et al. Paper.
Yeah.
I guess there are selection effects that you have to include in these estimates because for some values of the parameters, these sources can go out of the detector reach.
Absolutely.
How is this done for ET? Or in this paper, I don't know, do they include these?
They certainly include selection effects, but as is often the case, and as you know, the selection effects are often not discussed in detail because they're tricky to get right.
Yeah.
Okay. So they are included.
Okay, but we don't know exactly how.
At least I haven't managed to work out exactly how.
Okay, thanks.
Okay.
There is another question.
Yeah.
Can I?
Sure.
So from Anthony, maybe Anthony, you want to ask it directly? Maybe not.
Oh, so sorry. Yeah, I had a question asking about the distribution of intermediate black holes. Is that a theoretical value, or is it still, is it coming from observation? Because I remember
this one here.
No, the intermediate mass. Yes.
Yeah.
So,
This was a sketch I drew. It's not coming from anywhere at the moment.
Okay.
Sorry. In fact, in a second, I'm going to show you a similar prediction to the one in this paper. So the one in this paper, they use these stellar mass black holes, and then the second paper I'm going to whose results I'm going to outline, they use the intermediate these black holes, but they're going to assume this distribution is flat.
Okay. All right. No, thank you.
Okay.
There is another question, Isa.
It seems like a crazy idea, but I just, wondering, so you have the populations of the black holes, and also there you can then create the simulated the signal gravitational waves. I'm basically what I was wondering, if you somehow to simulate the observation and measure infer the redshift chirp mass, then can you actually do it in the reverse ways to actually cross-check whether your input models of the mass distribution could be correctly recovered based on the simulated observation? Or if that's useful enough, can we actually at some point later use that observation to actually infer the mass distribution given the redshift measurement?
So I need to think about your question, but what I would argue is that, in fact, what you would need to do is to extract your cosmological parameters and the mass distribution simultaneously, in the sense that it's not good enough to fix cosmology and study your mass distribution, which is what in fact is done here, right? In this LIGO-Virgo paper on the population of stellar mass black holes, this analysis is done fixing the Hubble constant. So I'm not sure if I answer your question, but what I would argue is that this analysis, you actually have to do it conjointly with the cosmological analysis. So you have to study your distribution as of letting H vary, H0 vary. I'm not sure that answers your question.
Okay, so then I guess my question really is, okay, if we somehow fix to this, lambdas in the particular cosmologies, and that can we actually do this exercise to see whether the populations could be inferred correctly? And it seems like it's a yes.
So, sorry, let me just say again, if you fix the parameters to Planck values, right, then you can study the populations. But then using those populations to then do cosmology is not the right thing to do.
Yeah, okay.
You have to study those populations, leaving cosmological parameters free, and infer them both.
Okay. Thank you.
And that's exactly what they're trying to do in this paper. Except for they've fixed the lower and upper masses. So in the second paper, which was somebody else's question, so this is another recent paper. This is not my work, so that's why it's not always easy for me to answer detailed questions on these papers, for example, about the selection effects. But in the second paper, they look at the population of intermediate mass black holes, so the ones above some minimum mass here, and they assume a uniform distribution above the minimum mass. And what they want to extract is the error on the Hubble parameter, so delta H over H, as a function of redshift, as a function of the minimum mass that they put. So again, the green here is Einstein telescope. So with Einstein telescope, they say that their errors were, of course, obviously much smaller than with LIGO Virgo, and they're essentially they're constant. They're independent of the minimum mass that they put. Okay, personally, I get tired after 2 hours teaching, so maybe I'm not going to go into more detail into that the result from this paper, but let me go on to some other predictions or forecasts with ET. This is from a recent paper by Belgasem and company in Geneva. And they, on the other hand, were not using the mass distribution, but they're focusing on binary neutron stars with electromagnetic counterparts as seen by ET. But the idea is, so the method is the same. You construct a simulated population. So here's their simulated population as a function of redshift. And then you try and determine how many of those, so this is for neutron stars, right? Of course, because you want electromagnetic counterparts. How many of those neutron stars will be observed in electromagnetic counterparts? And in fact, they have a realistic scenario which depends on the electromagnetic, so what telescopes will be available at the time of ET. And so here you see that the numbers are actually, if you initially have something like 80,000 gravitational wave detectors, BNSs, which are observing gravitational waves, the number which are observed with electromagnetic counterparts is very much smaller. And they claim that with about 10 to the 5 gravitational wave events with a signal to noise ratio of 12, realistically, about 100 to 200 will have an electromagnetic counterpart. And from there, they give constraints on the Hubble constant, H0, and on omega m. So you can see them here. And they also allow for the dark energy to probe, they also probe the dark energy equation of state. So I mentioned right at the beginning that with gravitational waves, we can probe the dark energy equation of state. And ET is allowing us to go to redshifts where we can actually really start doing that. And here they probe a standard equation of state, which is W, which is a constant, W0, which should be close to -1, plus a term in WA, which goes as Z over 1 plus Z. And you can see their predicted errors on W0 and WA. Now, this is for, I should have said it, this again is for a population of binary neutron stars, and they're assuming a distribution of binary neutron stars. So let's go back once more. Binary neutron stars are the green curve. They're assuming in that work that the population or the mass distribution of those binary neutron stars is known a priori. Okay? So they're not margining over unknown physics at this point. And then there's another paper which I just wanted to mention for those of you who are interested in the subject by Curie et al. And they've done something very similar, but they've taken not only a population of binary neutron stars, but also neutron star black holes, and assuming electromagnetic counterparts. And the advantage of adding a population of neutron star black hole binaries is that given that the black holes are heavier, then you can see them to larger redshifts. Okay, so you have more events, and also because they're heavier, you have louder signals to larger redshifts. And the long and the short of that paper is given in the two graphs that I've shown here. So this is the error on the Hubble constant as a function of the number of events. And this is the error on omega m as a function of the number of events. And they claim that with 600 events, they can get an accuracy comparable to the Planck accuracy on H0. Okay, so let me arrive at my conclusions. What I've tried to show you is that there are different ways to extract information on cosmological parameters using gravitational wave measurements. the crux of the matter is that the gravitational wave measurements give you the luminosity distance, which generally comes with an error, which is, unless there are higher order modes or precession, is difficult to minimize, unless you have a large number of events. You need information on the redshift from electromagnetic, which can come either from electromagnetic counterparts or from galaxy catalogs, and or through what known physics of, or possibly known physics of neutron star and binary black hole populations. So in other words, I think in the future, I think it's fair to say that cosmology with gravitational waves will go hand in hand with astrophysics. I don't think it'll be possible to separate these two fields. I think in the near future, at least with ET, we expect to have important results on measurement of cosmological parameters that should be able to resolve the Hubble tension. There are a number of effects which I haven't mentioned, but though I did try and sort of motivate them right at the beginning. With ET, you have to be a little bit careful because events such as the neutron star events last for a long time in your detector, so they're going to be most likely there'll be overlapping events. So during your 5 days of a neutron star wave in spiral, there'll be many black hole waveforms superimposed. That will have an effect on parameter estimation, which I think needs to be, people are certainly thinking about. And of course, this lensing error, which will need to be thought about a bit more. So generally, I think that parameter estimation with these third generation detectors is an important question for the future. There are other methods which I didn't mention to extract the redshift, but they were related to a question of Filippo before. If you have two neutron stars which are orbiting each other, so these are made of matter, they're going to be deformed. And that gives you a signal in the waveform, which is in fact dependent on the source frame mass, and therefore which can be used in a similar way to extract information on the distance measurement. And there have been predictions for that, but they're less, I think they're less, I mean, the prediction is a 7% accuracy in H0 with 10,000 events. And then for next time, before talking about the stochastic background, I'll also say a few words about how, with these gravitational wave measurements and measurements of the luminosity distance, one can extract information on modified gravity, and in particular on those theories which affect the propagation of gravitational waves. So that will be where the next lecture will take us before discussing the stochastic background of gravitational waves. So I'll stop there for today.
Okay, thank you very much, Dani. It was very nice, very clear.
If there are any questions, please go ahead.
Yeah, that's a good time for questions.
Okay, maybe, hi, I'm so sure. Yeah, I just rephrased I don't want to be a question, it's more like a comment, because I guess the answer is not super easy. So also it's just, what I had in mind, it was very clear, was just the following, that if H naught and the minimum mass of the parameter of the black hole are degenerate, given a mass distribution in the detector frame, how one can infer if there is really a black hole in the mass gap or not. That was.
Sorry, could you say that again? I'm having trouble catching your.
Yeah, so no, my question was like if, I mean, what I had in mind was a bit confusing before, was like if H naught and so the H naught that you infer from this analysis and the minimal mass of the black hole mass of the black hole distribution are degenerate, how one can infer from a given mass distribution in the detector frame if there is really a black hole in the mass gap or not, or is not just a different H naught, for instance. Okay, so just
yeah, I still don't get your question, but maybe I'm missing something. So you.
Okay.
You have a mass gap, right? In your source frame mass. And your question is, what happens if I observe an object which has a detected frame mass which is in that mass gap? Is that right?
So it could be just that you have a different H0, right? So
exactly, but that's exactly what you want to look at, right? That's exactly where you're going. That's exactly what the information you want to get. It's precisely those objects which you would observe, which are in your mass gap, which are going to give you information on H0.
Sorry, Danièle, I guess the problem that Jacopo is pointing out is that we also don't know what the value of the mass gap is.
So that's what I was saying.
He's saying you can shift in principle both, I guess. So
right,
they are degenerate.
Well, I can't argue. I'm not convinced that they're degenerate, but that's what I was arguing. You have to determine both simultaneously.
No,
yeah,
okay.
I agree.
I'm not saying that I'm degenerate because I'm completely ignorant in the subject.
I don't think they are degenerate, but
okay. That was my first question. Okay.
Okay. Sorry.
Thanks. Sorry for the.
Isang?
Yeah. If we use this gravitational wave experiment and measure the Hubble constant in an independent way, very high accuracy, but if the result turns out to be the case that is in between sort of the current Hubble tension, the value, right? And then how should we interpret this result? Or I mean, if the measurement is overlap with the CMB based measurement or the nearby universe measurement, that'll be nice. But if it's somewhere in between, how should we interpret the result?
Well, that's a question which I think you can get as many answers as you like, depending on who you ask, right?
Yeah.
Is your question what would be my interpretation of the result?
I understand. That's a kind of it depends on whom to this ask question, but yeah, it would be nice if you provide your perspective.
So my first perspective, I have to say, is one of total modesty, because the measurement of the Hubble constant using the distance ladder is a really complicated thing, and I mean they clearly understand their errors very well, but I can't judge on that. Okay. The sources of errors in there, I mean, there's so many astrophysical things that you need to know, right, on the luminosity of your objects. It's beyond my understanding, to be quite honest. So if one were to find a value of H0, which is precisely between, let's say, the CMB value and the supernova value, of course, I would wonder if there wasn't some kind of systematic error in the supernova value which had not been considered. Okay. If there isn't, then I would have a job understanding where it came from, because both are using late time physics, right?
Mm.
So then I would really have a job, I think.
Okay.
I don't know. Maybe Filippo would have a different answer then.
Yeah, I mean, useful to know. Thank you.
Maybe it's a bit late for. Okay, you have many people thanking you in the chat. Excellent talk, great talk.
Thank you very much.
Interesting and informative. So I think it's a good moment to stop. And we are convened this afternoon at 4 with Neil Cornish on gravitational wave data analysis, and with Danièle we are convened on Thursday.
Okay, bye everyone.
Thank you very much.
Ciao.